Can you hear me okay? Alex? How come you can't hear me? Alex, can you hear me?
Oh, sorry about that.
Oh, yeah. Okay. You can hear me now?
I had my volume down for some reason.
Okay. I've had that happen many a times. Okay. So which one do we want to look at first? Image one, or photo?
Image one. Pretty sure. Is it the graphing one?
It starts with problem 3.
Alright, it might be just image then. Whatever one has the graphs on it, I'm not sure.
Okay, that's probably the photo.
Oh,
This one here, fine?
Mm-hmm.
Okay. When we're graphing hyperbolic functions, in other words, let's talk about the parent function. Y equals 1 over x. That's the elementary function that we're talking about. First thing you need to decide here is your asymptote. You have a vertical asymptote, or you have a horizontal asymptote.
Okay.
The vertical asymptote is always the number that makes you divide by 0. In this case, it's x equals 0. So there's the vertical asymptote. The horizontal asymptote is always y equals 0 for a hyperbolic function. So those are our two asymptotes.
Oh, okay.
The hyperbolic function works is it approaches each asymptote from the first and the third quadrant.
Okay.
So this is the graph of y equal 1 over x. So the graph of y equal 3 over x is merely this times 3. So that would be what in terms of describing it? As
3 over a. Oh.
It wants you to state let's label at least 3 points on each side of the vertical asymptote. So let's find 3 points over on the right. And we're going to deal with, notice that the difference between 3 times this and 1 over x, that's a vertical stretch.
Okay.
The consequences of a vertical stretch are going to be like that.
Okay.
In other words, you can't really tell the difference. You can't tell the difference by looking at it, whether it's 1 over x or 3 over x. So let's find 3 points to the right of the vertical asymptote. Give me 1 point.
3,3 here.
Well, when x is equal to what? Well, find a value for x and figure out what y is. In other words, when x is equal to 3, y is equal to what?
When x is equal, y is equal to 1/3.
Not when x is equal to 3. We're dealing with the
it's equal
function.
to 1?
Yeah. Okay.
Okay.
So this point right there is 3, 1. Give me another.
Okay.
Give me another point.
Let's see. Be
We need 3 points. We need 3 points in this first quadrant here.
All right. It'd be
just pick values for x.
Half.
What they are.
1/2.
What if x is what?
If x is 1/2, it'd be 4. Or, yeah, if x is,
Okay, if x is 1/2, what is y?
wouldn't that move?
In other words, pick numbers that you can do the math on easily. If x is 2, what is y?
3.
What is y if x is 2?
3.5, or,
3/2.
oh, it is 3. Okay.
Huh?
You just
Now
put it like that.
now pick another number for x and tell me what y is.
Okay.
Doesn't really matter what number you pick. Just pick any number that we haven't picked already.
4.
Okay, what's y when x is 4?
3/4.
Okay, that's all we needed to do there.
Sorry, I just wasn't understanding.
That's okay. And they wanted 3 points on each side of the vertical asymptote, so we need 3 points over here on the left, so pick some negative values for x.
Could I just do the same numbers?
Yeah, you can, sure. She didn't specify, so this is -2, -3, -4, and -2, what's that coordinate going to be?
-3/2.
-3/2. And this coordinate is going to be,
-1.
and this coordinate is going to be,
-3/4.
okay. Now, state the equations of the asymptotes. What's the equation of the vertical asymptote? X equals 0. In other words, all vertical lines are x equals some number. In this case, the vertical asymptote is on the y-axis, and the y-axis is x equals 0.
Okay.
What's the horizontal asymptote?
Y=0.
What's the domain of this function?
-∞, 0.
Combined with?
0, ∞.
Correct. In other words, all real numbers except 0.
Yeah.
What's the range?
Same. Or
Yeah, pretty much the same. -∞ to 0, 0 to +∞. There's no way this function can ever be 0. There's no value of x that you can come up with that makes y 0. So,
it's just
yeah. So what's the transformation from the parent function?
a stretch of 3.
Vertical
Or vertical stretch.
Vertical stretch of 3.
Yeah.
Okay. Let's look at B. Hold on. Do you hear that noise in the background?
No.
No? Sounds like I don't know what that sounds like.
Is there a noise coming through my...
It's like a big woofer almost.
Huh.
So kind of I don't even know how to describe it. Not important.
That's interesting.
Not important. Okay, so if we're going to graph this, whenever you see the denominator has x in it like this,
Yeah.
it looks hyperbolic. Okay, in other words, the parent function is going to be y = 1 over x.
Okay.
So whenever we graph hyperbolic functions, the first thing we want to do is put the vertical asymptote in there. what's the vertical asymptote?
Is it -3?
Uh-huh. It's whatever makes this denominator 0.
Okay.
Okay, always.
So I just set that. Okay.
That's always how you get vertical asymptotes, is you can't have a division by 0. What's the horizontal asymptote? In other words, it would have been, it's normally y equals 0. But this has a vertical shift on it. So that shifts the horizontal asymptote also.
So +2? Or would it be a 2?
No, it would be right at +2. In other words, so here's our grid for graphing this thing. Okay. Now, a couple of other things that are taking place here. Let's first of all plot some points. So to the right of the vertical asymptote, give me 3 values of x and their corresponding values of y.
All right. I'll do just 3.
Yeah.
And then I'll work that out.
Okay. So when x is 3, what's y?
6. It'd be -1.
Okay, which is right here. Another point.
I'll just do 4.
How about x equals 0? Do the simplest calculations you can possibly get. X equals 0 is to the right of this vertical asymptote. So that's all that matters.
It'd be 0.
So it'd
be 0.
So when x is 0, y is 0.
Yeah.
One more point.
I'll do 1.
Do a point between 0 and -3, because we can kind of see what's happening here. This hyperbolic equation is going to look like this and like that. In other words, it's going to look just like a hyperbola, only it's now in the second and fourth quadrants of our grid. So what's the next point?
-1.
Okay, what's y equal to when x is -1?
-1.
Okay, that's that point right there. So there's our 3 points to the right of the vertical asymptote. How about 3 points to the left?
Would that be? I could do -4 or -5.
Yeah, that's fine.
-4.
It doesn't really matter whether it invokes fractions at this point or not, because we know what the curve looks like. So when x is -4, what do we have? We have
8.
Okay, so when x is -4, we have 8. So -4 comma 8. How about another one?
Let's see. Or wait, that would be -5. And then
What's y when x is -5?
That'd be -2. Should be positive. Should be 5. Oh, 5. Yeah.
Okay. One more point. Don't stop now. You're on a roll. -6.
Yeah, 2 would be 4.
Okay. So now we have 3 points on both sides. We can see for sure what the thing looks like. What's the equation of the vertical asymptote?
X equals 3 or negative 3.
X equal -3.
Yeah.
What's the equation
Y equals
of the
2.
horizontal asymptotes? Okay. And let's see, what else did they want here? They wanted domain, range, and transformations. What's the domain?
It'd be negative infinity, -3.
Combined with
-3 to, and then -3 to positive infinity, yeah.
so that's the domain there. The range,
No, negative infinity. +2. And then +2 to infinity.
okay. And the transformation. We've got actually 3 things going on here. We've got a horizontal shift, we've got a vertical shift, and we have a vertical stretch.
Okay. So vertical shift. Oh.
So the vertical shift is up 2.
Yeah. And then vertical shift left 3.
Horizontal shift left 3.
Oh, all right. And then vertical stretch of 6.
And what else? There's one more thing going on here.
Reflection.
Reflection over the x-axis.
Over the x-axis. All right.
In other words, if I make this a positive sign, these 2 curves come in these 2 quadrants, which is the reflection over the x-axis. Okay. I'm going to look at C next.
Yeah.
It's the vertical asymptote.
X equals 3.
What's the horizontal asymptote?
1.
Good. Because we have the same power in the numerator for x as we do in the denominator, therefore the horizontal asymptote is the ratio of their coefficients. So that's how we got y equal 1.
Okay.
If I would have made it like this, then the horizontal asymptote would be y equal 2. Just whatever the ratio of the coefficients are.
Okay.
Now, I know that this is either going to be this way, or this way. Hyperbolic equations are always going to be like that.
Okay.
So let's figure out which quadrants we're in. So let's go ahead and figure out at least one point and figure out which quadrant quadrant it's in. Because right off the bat, when I look at that, I don't know if it's first and third or second and fourth. But we can determine it by finding a value. Let's find a point. Pick a value for x to the right of the vertical asymptote.
I'll do just 4.
Okay.
So it'd just be 5.
Okay, so when x is equal to 4, y is equal to 5. That tells us immediately where we're at. And in fact, from that information alone, I can graph this. Without 3 points. Because all I needed was 1 point to tell me whether I was in the first and third quadrant of my grid or the second and fourth quadrant. And this point right here clearly put us to the right of the vertical asymptote and above the horizontal asymptote. So to answer the question where she wants 3 points, we still need to find 3 more points. But I'm going to let you do that. I'm going to let you do that. Just because we don't need to be spending our time doing that.
Yeah.
What is the equation of the vertical asymptote, x equals 3? What about the horizontal asymptote?
Y equals -1.
Y equal 1.
Or 1, yeah. Okay.
Positive 1. What's the domain?
Negative infinity to 3. -3, or yeah, to 3.
Okay.
Okay.
You could also state it as all reals except x equal to 3.
All right.
Might be an easier way to state it. I don't know if your teacher is going to allow that or not, but that's the problem. I mean, you could state it that way. What's the range?
Can I just state it that way for that?
Uh-huh. Certainly for me, you can.
Yeah, he'll allow it.
So the range is what?
All real numbers except for 0.
All real numbers
except
except
for 1.
y equal 1. You have to state it that way. In other words, if you're going to state the range, it needs to be all reals except y not equal to 1. In other words, that's the same as saying negative infinity to 1, comma, combined with 1 to positive infinity.
Okay.
Okay? Okay, let's see. State the transformation.
I had a horizontal shift right 3 and a vertical shift right 1 maybe, or a vertical stretch of 1.
In order to determine this, right offhand from our graph, it looks like a horizontal shift to the right of 3 and a vertical stretch of 1. But I can't really tell that from looking at this equation. So let's divide it and see what we get.
Semi-full.
So this is what we got. We got 1 and 4 over x minus 3. So I can write that like this. Now, I don't want to erase any of this. In other words, instead of writing it x plus 1 over x minus 3, I go ahead and do the division. I get 1 with this remainder. Well, I can write that as 4 over x minus 3 plus 1. Now I can read everything that's important about the transformation. I've got
Okay.
a
All right.
horizontal shift to the right of 3. I got a vertical shift up of 1. And I got a vertical stretch of 4.
Okay. Wow.
So
Yeah, that.
I wouldn't have been able to come up with that vertical stretch without doing this division. There's no way I would
Okay.
have
Is that
figured
just
out the
different
vertical
forms?
stretch was 4. What's that?
Is that just different forms
What do you mean?
of the equation?
Well, what I basically did was I took x plus 1, I divided it by x minus 3, and I got 1 plus a remainder of 4 over x minus 3. Well, this is in the form of transformations. This is not.
Okay.
I can't tell
Yeah.
transformations from looking at that. I mean, I can tell the horizontal shift, but I can't really tell anything else. Once I've divided this into that, separated into a whole number plus this, now this is real easy. 4
Yeah.
over x minus 3 plus 1, well, the plus 1 is a vertical shift. The 3 is a horizontal shift, and the vertical stretch is that 4.
Yeah.
So when they're complicated like that, you have to do that division. Now
Okay.
D they gave it to us like that. Notice.
Yeah.
D is already in that format. So to do this, we can do a couple of things. Let's do the transformations first.
All right. So vertical stretch of 4. And a horizontal shift right 2. And then is that a horizontal shift down 1?
A vertical. Whenever the number
Vertical.
comes at the end,
Okay.
it's always vertical. Well, it doesn't really matter whether it's at the end or not. In other words, they could have put it up front, minus 1 plus this, and it would still be a vertical shift of 1 down.
All right.
Okay, so we got all the transformations. Now let's plot it. Where's our vertical asymptote?
2.
Where's our horizontal asymptote?
-3.
What would the horizontal asymptote be if I didn't have this minus 1? If I just had 4 over x minus 2?
-2.
No, it would be 0. Remember, the horizontal asymptote is always y equals 0 if the power in the denominator of x is greater than it is in the numerator. And there isn't
Okay.
a numerator. So our horizontal asymptote for this part right here is y equals 0, but since everything is moved down by 1, the horizontal asymptote has to be y equals minus 1.
Okay.
Now let's pick one point to the right of the vertical asymptote and figure out which quadrant it's in.
Okay. Just plug in, and it's going to be to the left.
To the right of the vertical asymptote. Find a value of x that's to the right of that vertical asymptote.
So 3 minus 2. 3, or 3 and 3.
3 and 3. Okay, so that puts it smack dab right there. Now we know everything we need to know. Again, I'll let you find 2 other points, but I know the graph is asymptotic with these 2 asymptotes. by just plotting that one point that pinpoints it in that first quadrant, which means the other half of the graph has to be in the third quadrant. Okay?
All right.
All right, let's see. What else do we got here? Oh, let's see. There was one more document. Should we look at this one?
Yeah.
So how are we going to do this?
Let's see.
Whenever you're doing problems like this, if you can factor, factor. Always.
Okay.
Every time. So what can I factor out of the left term?
1 second. Out of the left term.
Out of the left term's denominator, what can you factor out of there?
Oh. You factor 3 up.
Okay. Out of the right term.
X minus 2.
Out of the right term's denominator, factor that for me.
You could take X out.
Yeah?
X out.
Yeah, no, that's called what? The difference of... It's difference of squares? How does difference of squares factor?
Okay. X minus 4 and X minus 2 and X plus 2.
Right. Okay. Now we have a pretty good idea of what we need for a common denominator. What's our common denominator going to be?
X minus 2.
Okay, common denominators need to be divisible by every term. In other words, whatever we use as a common denominator has to be evenly divisible by that and by those two. So it's the bigger one that we need as a common denominator. It can't be x minus 2 because this doesn't divide into x minus 2.
Okay.
However, how about this as a common denominator? Notice that this term divides into that perfectly, and this term divides into that perfectly. And it's the lowest thing that does. So there's my common denominator. Now how does the numerator have to read to give me this denominator on the left?
Sorry, say that again.
What do I need in the numerator on the left so that this equals this? 1 second, if you would, Alex. Maybe somebody can do something. Yeah. Absolutely. I was going to call you as soon as I was out of my session here and ask you whether it was going to be online or in person. So that's fine. I will just text you the meeting ID at 8 o'clock. All right. Talk to you then. Bye-bye. Sorry about that. Okay, so our goal, once we found a common denominator, we have to figure out what the numerator needs to be. In other words, I can't change this fraction. I can only state it in a different way. So what's the new numerator have to be?
1x, or just x? X plus 2.
Yeah, notice
Oh,
that.
because that, oh, okay.
In other words, what I really had to do, let's go back and look at this, because this is really, really key. What I really had to do to this fraction is multiply it by x plus 2 divided by x plus 2. Notice that that's the number 1. You can multiply any fraction by the number 1 without changing its value. So I'm going to multiply that by x plus 2 over x plus 2, and it gives me this.
Okay.
What do I have to multiply
That makes
this by in order to produce this denominator?
3.
3 over 3.
3x.
3 over
3
3.
over 3.
Yeah,
Okay.
because I can only multiply it by 1. So I have to multiply top and bottom by 3, and that gives me 3x in the top. And it gives me the 3 in the bottom that I need. But that's the process whenever you're adding or finding common denominators for fractions like this. Okay, now we can operate on the numerator. In other words, we still have one last step we can do here. Our final answer is going to have this common denominator. But what is the new numerator?
Negative 2x plus by 2.
Exactly. And that's the answer.
Okay.
I mean, you could maybe factor out a negative 2 from the top. Not sure that really does any good. In other words, I could make the top look like this. But that doesn't really simplify anything.
Yeah.
Okay, let's do another one of those.
It's pretty much as simple as it.
Okay, let's solve number 5.
All right.
X minus 4 over x minus 1 equals 10 over x plus 7. Check for extraneous solutions. Okay?
All right.
It's our first step.
You gotta get common denominator.
Well, not really. Not really. We want to get rid of the denominator. So
Okay.
let's cross multiply. That'll get rid of the denominators in one step.
Oh, okay. That makes sense.
Okay, so when I cross multiply, what do I have on my left?
You're gonna have x squared minus 4x minus 28.
Don't forget the 7x. Plus,
Oh yeah, plus the 7x.
remember, you're foiling it, so there should be 4 terms.
Yeah.
F, the O, the I, and the L. On the right side, what do we got?
10x minus 10.
Now combine everything. We can see that we're looking at a quadratic.
Yeah.
So we don't want to put the variables on the left and the numbers on the right. We want to put everything on the left.
Okay.
What do we got here?
So it's gonna be negative 7x. Minus 18.
Where are we getting 18? Oh, this is 10? Yes, excuse me, I must have erased that.
Oh yeah, that's right.
That's okay. So can we factor that?
Yeah, it'd be x minus or plus 9 minus 2.
Okay, notice that that's not going to give you the correct middle term. Here, the way we want to do this is we want factors of 18 that subtract to the number 7, and we want to put the biggest factor with the sign of the middle term. So I don't want to put the 9 there and the 2 there. I want to put the 9 with the negative sign because the negative sign is in the middle term. And that gives us a middle term of minus 7x.
Oh, yeah. That would have given us a positive. I don't know why I was thinking that.
Right. So my solutions are x equal minus 2 and x equal 9. Does either of those solutions present any problems? Well, we probably ought to plug it in and make sure that both of them work. So when you put in minus 2, what's the left become? What's minus 2 minus 4?
Negative 6. So
What's minus 2 minus 1?
This would be 2.
Okay, so that's 2. Is that equal to 10 over negative 2 plus 7?
No, so it'd be, no.
Yeah,
sorry.
Yeah, it is. So negative 2 works. How about 9?
5. 8. 5 over 8. 16. Yeah.
Is that true?
Yeah.
Okay, so both of those work.
So no extraneous.
Yeah, there weren't any on that one. Extraneous solutions can come from it no longer works. In other words, when you stick it in, it's no longer an equation. Or it can come from if the denominator ends up being 0, that can't be a solution either.
Okay.
In other words, I would not be able to have a solution of x equals 0 for this. But let's do this. Let's cross multiply. Give me the next line.
Nine x squared minus 27x. And then 3x cubed minus 18x squared plus by 27x.
Okay. Now notice that we don't have any constants here. So even though we have a cubic, we're going to be able to factor out an x and have x times some quadratic. So first of all, let's combine all the like terms, put them on one side, and tell me what to write. How many x cubes do you have?
3.
Okay, so we're moving everything that direction. How many x
Minus
squared do we?
Oh, yeah.
How many x's?
And then none.
Actually, 27x plus 27x is 54x.
Oh, 54.
And now we have it like that.
Oh, yeah.
Okay, now let's factor some stuff out. What's the greatest common factor that we can pull out of there?
Would it be 3?
3x.
3. Oh, yeah, 3x.
And it's very important to get that x out of there because we want a quadratic left behind. Because we can factor a quadratic. We don't know how to factor cubics. Okay?
Okay.
Now factor this quadratic.
All right.
Did they really give us one that...
3 and 6. So it'd be
Oh, good. Yeah.
x minus 3 and x plus 3.
X minus 6.
Or x minus 6. Yeah, not.
In other words, this tells you that they have to both have the same sign.
Yeah.
And this tells you that they both have to be negative. Okay. So that's equal to 0. So what are my solutions? There should be 3 of them, because we started with a cubic.
So it'd be x equals 3, x equals 6, and then
You have three numbers multiplied together that are equal to 0. Either of the 3 can be 0. So what's the third solution?
wait, either.
In other words, either this can be 0, this can
Okay.
be 0, or that can be 0.
Okay.
So the third solution is x equals 0
Okay.
for this part over here. However, when we go back and start plugging those in,
Oh, you
notice
said that wouldn't be able to.
notice that x equals 0 is not going to work, because that's going to make this denominator 0. Immediately I can rule that one out.
Okay.
So let's check the other two. X is equal to 3. What do we have? We have 9 over what?
9 over 9 minus 18 plus by 3. Or plus by 9.
Ah, that's a problem also.
0.
So x can't be equal to 3 either.
Nope.
Well, let's make sure we actually have a solution that works here. Let's try x equals 6.
Um, 36 minus 36 plus by 9.
Okay.
So yeah,
Well, we haven't proved it works yet. We got to plug it into the other
plug
side.
it into the other side. 18 over 36 minus 18.
So this becomes 9 over 9 equals 18 over 18.
Yep.
Yes. So 6 is a solution.
Okay.
That was a good problem, because it gave us 2 solutions that weren't really solutions. They were both extraneous. All right, I think we got time for one more here.
All right.
Now, when you see a problem like this, know that it's a factoring problem.
Okay.
What are my likely factors of this denominator on the right side? Just by looking at the problem. What do they figure to be? Right? How did I know that? I didn't factor that to get that. I knew that because I knew one of the factors would be that and the other factor would be that. That's just the way they give you the problems. But it does break into that. Notice that it gives us minus 3x as the middle term. So now we have an unusual situation where we have an equation that has 3 denominators in it.
Okay.
And we'd like to come up with a way that we can get rid of all 3 denominators in one stroke. This is slightly different than finding a common denominator. When we find a common denominator, we're only allowed to multiply each fraction by the number 1. When we're doing this technique, I'm going to multiply the whole left side of the equation by something and the whole right side of the equation by something.
All right.
What's that something going to be?
And then I'm going to times it by it.
I'm going to multiply everything by that product right there. Notice what happens. When I multiply the left term of the left side by x minus 1 times x minus 2, multiply this term by x minus 1 times x minus 2, and multiply this side by x minus 1 by x minus 2, look at how pretty everything works. This cancels with that, so I'm left with x times x minus 2, or x squared minus 2x.
Oh, and then that one cancels.
This cancels that, so I'm left with, in parentheses, x minus 1. Very important to put the parentheses there. Otherwise you get the sign wrong on this number. And then on the right side, they both cancel with both, so I'm simply left with this. So I took this horrendous looking thing that had 3 different denominators, and I got rid of all of them in one step by essentially multiplying both sides by the common denominator, if you want to put it that way. So now, if I simplify and put everything on the left, what have I got? I got x squared minus 3x plus 1 minus 2x plus 5 equals 0. So what is that? X squared minus 5x plus 6.
Yeah.
Back through that.
Minus 5x plus 5x. That would be x minus 3 and x plus 2. Or x minus 2 is a positive. Okay.
So
just like
x is equal to 2 or x is equal to 3. Which one of those presents a real big problem?
2. X equals 2.
So I can't use that as a solution, because that makes this 0. Division by 0. So let's try x equal 3. Make sure we have a, so we have 3 over 2 minus 1 over 1 equals 1 over, let's see, 9 minus 9, that. So we got 3 halves minus 1, which is equal to 1 half equals 1 half.
Yep.
So we got a solution.
So x equals.
But this shows you how you really have to check all your solutions. Because at this level, especially when you're talking with quadratics, whenever you have quadratics in the equation, there's potential to have, actually whenever there's variables in a denominator, you want to check. Because you could be dividing by 0, like we were in that one.
Yeah, just double check that real fast because it's faster.
Yeah. Okay, let's call it a session.
All right, sounds good. Thank you.
Let's see, we have another one tomorrow, correct?
Yeah.
You still want that one at 5:15?
I probably won't need the whole thing though.
That's fine. We can go as long as you want. Doesn't matter.
All right, cool. All right.
I will see you tomorrow.
All right, sounds good. Talk to you later.
Okay, bye-bye.